Okay, in today's lecture, we're going to cover the last part of our section 6.6 material on surface integrals. And in this last part of the lecture, we're going to discuss surface integrals of vector fields. So last time we had defined the surface integral of a scalar function of three variables over some surface S in space. And today we're going to extend that definition to the surface integral of a vector field over some three-dimensional surface. Now, before we can define a surface integral or come up with the formula for how to calculate it, we need a little terminology. So let's introduce some definitions to start with. So here we will say that a surface S is said to be an oriented surface, or sometimes called an orientable surface, if it is possible to choose a unit normal vector n at every point xyz on the surface such that n varies continuously over that surface. Now, in the event that S is an orientable surface, the choice of our unit normal vector n at any given point on the surface is said to provide that surface S with an orientation. So for any orientable surface, there are two possible orientations of that surface. To explain this a little more clearly, let's look at some visual aids. So let's suppose that we have some surface S shown here in blue. So this is our surface, we'll call it S. This is said to be an orientable surface if for every point that lies on this surface, I am able to choose a unit normal vector, that is a vector n, which is normal to the surface. That is, it's the normal vector to the tangent plane of that surface at any point. And this normal vector varies continuously over that surface S. So the orientation that is being shown here would be called the upward orientation. And we could alternatively, for the same surface, choose for any point on our surface S a downward pointing unit normal vector n. And we would have this orientable surface which provides the downward orientation. And we'll see that the direction of our orientation will affect how we're going to calculate a surface integral and what these different orientations might represent physically. Now, in certain problems that we consider with surface integrals, with vector fields, we'll be integrating the vector field over a closed surface. So let's define what we mean by a closed surface. So a closed surface is any surface which would be defined as the boundary of some solid region E in space. So as a simple example, we could consider, say, a sphere centered at the origin of some arbitrary radius. And this would be an example of a closed surface. It's the boundary of a ball centered at the origin of a given radius. So any surface which is the boundary of a solid region is said to be a closed surface. And these closed surfaces, most of the time, are orientable. In our course, all the surfaces we work with will be orientable. And the convention that we use for a closed surface is that the positive orientation is the one for which our unit normal vectors will point outward from the solid region E. So what we have here in this left-hand figure for our sphere is a set of unit normal vectors for given points on our sphere. We call these vectors n. And since these vectors are pointing outward from the unit ball or outward from the sphere, this is said to have the positive orientation. Whereas if we were to take that same sphere and for the same collection of points look at the unit normal vectors pointing inward from the surface, then this would be said to have the negative orientation. So the negative orientation is where our normal vector is pointing inward. So as I mentioned, any of the surfaces that we're working with in our course will be orientable. They're relatively nice surfaces. And just to illustrate that not every surface is orientable, what would be some examples of non-orientable surfaces? So the classic example is what's called the Mobius strip. So we can think of it as being constructed as a rectangular strip which is rotated lengthwise by 180 degrees and then glued at its ends. So we have a self-intersecting strip here called the Mobius strip. And the reason that this is not orientable is that if we choose vectors, say for some point on this strip, a unit normal vector, as our points vary over this strip, and we keep choosing these normal vectors, eventually we get a normal vector at the same point, but which is pointing in the downward direction here. So we end up with a surface which is non-orientable. Another example of a non-orientable surface, which would be a closed surface, is the Klein bottle. So that Klein bottle is shown in our right-hand figure here. It's an example of a closed non-orientable surface. We can think of it as a bottle which intersects itself. So here, just a couple of examples to illustrate that not every surface is orientable. Let's think about how we could define a surface integral of a vector field over such a surface. So here's our definition. If we have some continuous vector field f, which is defined on an oriented surface S, with a unit normal vector n, so since this is orientable for any point on our surface, we can choose a unit normal vector, either with the positive or negative orientation, and we would define the surface integral of that vector field f over our surface as follows. So first off, the notation is similar to what we saw for a surface integral for a scalar function. We denote it as a double integral with a subscript s to denote the surface. And then we have our boldface f to denote the vector field f, dot d boldface s. So this notation is used for the surface integral of a vector field, and it is defined as the surface integral over the surface S with respect to surface area of the scalar function, which would be the dot product of our vector field with this unit normal vector, n. Now this integral is also commonly called the flux of that vector field across the surface S. So you'll see several homework problems or maybe a final exam problem that would ask you to calculate the flux of a field across a surface. So when we see flux, we know it's referring to this surface integral of that vector field across our surface. So before we derive some formulas for how to calculate flux more easily, let's think about what this flux integral is representing. So here, let's suppose that we have a surface S. Let's say maybe it's not closed, but we have some upper part of a hemisphere or something in a space. So what we're doing when we're calculating a flux integral of a vector field is we're adding up the values of the vectors f acting in the direction of the normal vector in, and then integrating over the surface. That is, we're adding up the values of our vector field acting in the direction of our normal vector. So for the surface S shown here, let's suppose that we have the positive or outward orientation. So for different points on my surface, I'm choosing my unit normal vector to be in the upward direction. And let's say that we have a vector field, F, which is continuous over that surface. So remember, the graph of a vector field in space is a collection of arrows. An easy way to think about this physically is maybe this vector field represents a velocity field of some fluid moving through 3 dimensions. So at any point on my surface, I have my fluid velocity is acting in some direction. Maybe we have flow inward and outward at different points with different magnitudes. So what my surface integral is representing is the sum of these green arrows acting in the direction of the unit normal vector in over this surface. So we can think about this flux integral as measuring the rate of flow of our fluid through this surface S. So if the surface maybe represented a net that we had placed in some fluid, submerged it in some fluid, which is flowing through this net, this flux integral is measuring the rate of change or the rate of flow of that fluid through this net, which would have the shape of our surface S. And we can see from the way that we've drawn these velocity or vector field arrows that for some points, the velocity field might act in a direction opposite of the unit normal vector. That is, if we have the upward unit normal, for some points our velocity vector is flowing downward. At other points it's flowing upward. So we're going to have some points where our fluid field is acting against the direction of our normal vector, and some where it's flowing in the direction of that normal. And that difference will be denoted by a sign change. If we're acting against the direction of our normal vector, then we would have a negative flux. If we're acting in the direction of the normal vector, then we would have a positive flux. So now that we know how this flux integral is defined and what it represents, or what it could represent, let's think about how to find a flux integral for a vector field in general over a surface which is the graph of a function. So here, let's suppose that we have a vector field F in space whose component functions are P, Q, and R of X, Y, and Z. And let's suppose that we have a surface S, which is the graph of some function. So maybe it can be considered as the graph Z as a function G of X and Y, where X and Y are in some domain D in the plane. So here we are told to use the definition of this flux integral to find a formula for the flux of F across our surface in terms of these component functions and the function G, which defines our surface. So one way that we can proceed here is by thinking about our surface as a level surface. So let's start by saying that our surface S is a level surface of some function F, which we could describe as having the form F of X, Y, and Z is equal to Z minus G of X and Y. So if our surface is being described by the equation Z is equal to G of X and Y, then this difference, Z minus G of XY, would have to be 0. So we can think about defining this surface alternatively as the level surface of some function f, where f is the function defined as z minus g of x and y, which is then equal to a constant 0. Now, what we need to do in order to use this definition of the flux integral is find a unit normal vector in to our surface. Now, if we're working with level surfaces, we can recall that one property we had for the gradient vector is that the gradient vector of a function is normal to the level surface of that function. So here, let's say the gradient vector, that is grad of f, is normal to the surface S. So if we want a unit normal vector in, recall in our definition of the flux integral, n is a unit normal, then we can take our gradient vector f and divide through by its magnitude. So here a unit normal vector is given by, let's denote it as n, and we could find it by taking grad f and dividing through by its magnitude. So let's see what we have here. For our numerator, we're taking the gradient of f, and the first component of the gradient vector is going to be the partial derivative of this function f, which was z minus g of xy, differentiated with respect to x. So the partial derivative with respect to x gives us negative the partial derivative of this function g with respect to x. Our second component is the partial derivative of f with respect to y, which would give us the negative of the partial derivative of g with respect to y. And our third component is the partial derivative of f with respect to z. Well, we had z minus g of xy, so our partial derivative with respect to z is 1. And then we're dividing through by the magnitude of that vector, which would be the square root of the sum of the squares of its components. So that is the sum of negative g sub x squared, negative g sub y squared, and 1 squared, which is 1. So we have the following unit normal vector for any point on that surface S. Now, one thing to make note of here is that the last component of this normal vector, that is 1 over the square root of this expression, this is our k component, which denotes the direction or the motion in the z direction. So notice that this k component is positive. So this corresponds to the outward or upward unit normal vector. So here we have the upward orientation for the given unit normal. So once we have our unit normal vector field, we're ready to use the definition to find our flux integral. So here, the flux of this vector field across the surface is the following. And it's calculated as the surface integral over the surface S of our vector field F dot product with the unit normal vector integrating with respect to surface area. So let's look at this dot product that we have. So we will have the surface integral over S, and we're taking the dot product of F with our unit normal. So let's look at this here. Recall that F was the vector field whose component functions were P, Q, and R. And our unit normal vector is this vector n, whose components were negative g of x over this square root term, negative g of y divided by this square root term, and then 1 over that square root term. So taking the dot product, let's see what we have. For our first component, we're going to multiply our first component function, which was p, times the first component of our unit normal vector, which gives us negative p times the partial derivative of g with respect to x over the square root of negative g sub x squared plus negative g sub y squared plus 1, plus for the next terms in our dot product, we have q, the second component of our vector field, times the second component of our unit normal, this negative g sub y divided by that square root term. So that gives us negative q times the partial of g with respect to y divided by this same square root term that we had. And then plus for the last component of our dot product, we have r times 1 over that same square root term. So that is plus r divided by the same square root term in the denominator that we use to normalize our vector field. And then we're integrating this with respect to surface area. So recall that to evaluate a surface integral over a surface S, which is the graph of a function, we would take the following. We would convert this to a double integral over the region D, where D is the projection of our surface onto the xy plane. And we would take our function, which we just found was negative p g sub x, negative q g sub y plus r, over the square root of, if we square these expressions, we can forget about the negatives inside of the parentheses. So I would have the partial of g with respect to x squared, doesn't matter if it's a positive or negative being squared, plus the partial of g with respect to y squared plus 1. And then this differential of s, when we convert this to a double integral with respect to area, becomes the square root of 1 plus the sum of the squares of the partial derivatives of the function which defines my surface. Now here our surface was the graph of g of xy, so we have the square root of 1 plus g of x squared plus g sub y squared, integrating with respect to area then. So we see that this square root of 1 plus the sum of the squares of the partial derivatives will cancel, and we arrive at the following. So our flux integral of this vector field over the surface S can be converted to a double integral over the plane region D, which is the projection of our surface onto the xy plane. And the function that we're integrating is negative p times the partial derivative of g with respect to x, negative q times the partial derivative of g with respect to y, plus r, where p, q, and r are the component functions of our vector field. And then we're integrating this with respect to area. So this is a formula to calculate the flux of a vector field over a surface which is the graph of a function. And one thing to note is that here in this normal vector that we found was the upward unit normal. So remember, we had this upward orientation because the k component of our normal vector n was positive. So if our surface was made to have the downward unit normal, or the downward orientation, we would just multiply this expression for our flux by a negative 1 to change the direction of our unit normal vector. So now that we have a way to calculate flux by converting to a double integral, let's look at some examples. So in this first example of calculating flux, we are asked to find the flux of this vector field, whose component functions are given, across the part of the paraboloid, z equals x squared plus y squared, so circular upward opening paraboloid, that lies above the square, where x ranges from 0 to 1 and y ranges to 0 to 1, and which has the positive orientation. So let's think about sketching our surface here just to get a visual. So in space, we have our coordinate axes, x-axis, y-axis, and z-axis. And we're looking at part of a paraboloid, z equals x squared plus y squared. So that is a circular paraboloid whose vertex is at the origin and is opening upward. Its cross sections with any horizontal plane parallel to the xy plane is a circle. And cross sections with planes parallel to the xz or yz planes give us parabolas. So we have a surface S that looks like this, and it's given the positive orientation. So for any point on this surface S, we're looking at the upward orientation. And we're looking at just the part of that surface S which lies above some rectangular region in the xy plane, where x ranges from 0 to 1 and y ranges from 0 to 1. So we only care about the part of that parabola, paraboloid that lies above this plane region D. Let's think about what we would need to calculate this flux. So we just derived a formula for this flux integral if our surface S can be described as the graph of a function of x and y, which here it is. We've got our surface is the graph of x squared plus y squared. So let's start by giving that function a name. Here, let's say z will be g of x and y, which is defined as x squared plus y squared. So using our new formula for flux, we would have the flux is defined as this integral of our vector field f across the surface S. And to calculate it, we convert this to a double integral over the square D, that is the projection onto our xy plane. Here we were told we're only interested in the part of our surface lying above that square. And the function that we're integrating is defined as the negative of p, which is our first component of the vector field, so in this case e to the y, times the partial derivative of g with respect to x, which would be 2x, minus q, so the second component function of our vector field, which is y e to the x, times the partial derivative of g with respect to y, which is 2y, plus r, which is the third component of our vector field. Here, x squared times y, integrating with respect to area. So to evaluate this double integral, we'll set it up as an iterated integral. And we have the integral from 0 to 1 in the x direction and 0 to 1 in the y direction to define our square d in the xy plane. And let's simplify our function that we're integrating a little. So rewriting this, we have negative 2x times e to the y minus 2y squared times e to the x plus x squared y, and then integrating in the order dy dx. Here it doesn't really matter which order you integrate in. Neither order gives a particularly easier integral. So starting by finding our antiderivative with respect to y, we have the integral from 0 to 1 of negative 2x, antiderivative of e to the y is e to the y, minus antiderivative of 2y squared would be 2/3 y cubed times our constant e to the x, and then plus antiderivative of x squared y with respect to y would be 1/2 x squared y squared, where we're evaluating from y equals to 0, 1, and then integrating with respect to x. So let's see what we get. We've got the integral from 0 to 1 of, when we evaluate at y equals 1, we have negative 2x times e, or I'll write it as negative 2e times x, minus a 2/3 e to the x plus 1/2 x squared. And then we subtract what we get when we plug in 0 for x. Plugging in 0 for x, we have this term is, 0 for y. So plugging in 0 for y, our first term gives us a negative 2x. So subtracting the negative 2x is a positive 2x. And then plugging in 0 for y, the second two terms are 0. So we just have that plus 2x term. And now we integrate with respect to x, and we have, for our antiderivative, negative e times x squared minus 2/3 e to the x plus 1/6 x cubed plus x squared, evaluating from 0 to 1. So when we plug in 1 for x, we have negative e minus 2/3 e plus 1/6 plus 1. And then we subtract what we get when we plug in 0 for x. So plugging in 0 for x, well, this first term is 0. Our second term is negative 2/3. So subtracting that, we have a positive 2/3. And then our last two terms, if x is 0, are both 0. So we have the following. And then grouping like terms, we had a negative e minus 2/3 e. So that is minus 5/3 e. And then grouping our constants, we have, let's see, 6 plus 1/6 plus 4/6 gives us 15/6, or 5/2, I believe. So this would be the value of the flux of that vector field over this surface S. Okay. So let's look at another one. So before we look at this next example, which will be a flux integral over a closed surface, let's think about how we could define or extend our definition that we had for a flux integral over a surface to a closed surface. So let's suppose that we have a surface S, which is piecewise smooth. So maybe it has some corners on it or sharp edges, but it can be decomposed into a union, or that is a finite union of smooth surfaces. So here let's say that S is the union of a few pieces, S1, S2 up through Sn, where each of these subsurfaces, S1, S2 up through Sn, are smooth. Then we would define the surface integral of that vector field f over our surface as follows. So that flux integral, or the surface integral of our vector field, would be defined as the sum of the flux integral of f over the surface S1 plus the flux integral over the surface S2, and so on, up through the flux integral of our vector field f over the surface Sn. So that is, we would have to compute the flux over each of these subsurfaces, S1, S2, up through Sn, and then sum them to get the flux over that surface itself. So now that we have this extension of our flux integral to piecewise smooth surfaces, let's look at an example making use of this. So here we are asked for the outward flux of the vector field F, whose components are x, y, z, across the boundary of the region enclosed by the paraboloid, z equals 4 minus x squared minus y squared, so downward opening paraboloid vertex at 0, 0, 4, and the plane z equals 0, that is the xy plane. So let's think about sketching our surface here. So we have the surface, which is the boundary of a solid region enclosed by the paraboloid, z equals 4 minus x squared minus y squared. So some downward opening circular paraboloid, vertex at 0, 0, 4 in space. And the plane z equals 0, that is the xy plane. So this downward opening paraboloid will eventually intersect the xy plane in a circle. To find the particular equation of that circle of intersection, we would let z equal 0. If z equals 0 is substituted into the equation of our paraboloid, we have 4 minus x squared minus y squared is 0, or x squared plus y squared is equal to 4. So that would be our circle in the xy plane, centered at the origin of radius 2. So our surface S is this closed surface consisting of this top piece of our paraboloid, which lies above the xy plane, and the bottom disk, that is the part of the xy plane which lies within this disk of radius 2 centered at the origin. So our surface S here can be thought of as the union of two piecewise or two smooth surfaces, let's say S1 and S2, where S1, let's call the upper half of this paraboloid above the xy plane, and S2 will denote this disc-shaped region, which is the bottom of our solid. So let's think about how to calculate our flux over this surface. Here we were asked for outward flux. So on S1, we are taking the upward unit normal. And on S2, if we're interested in the outward flux, we would be taking the downward or negative unit normal. So in order to calculate this flux, we have to compute the flux over each part of this surface, S1 and S2, and then take the sum. So let's start with S1. So here, let's say first, S1 is the graph of the function g of xy, which is 4 minus x squared minus y squared. And so if we want to calculate the flux across S1, we would set this up as a double integral over the region D, which would be the projection of our solid S1 onto the xy plane. So that is the surface S2 itself, this disk. And the function that we're integrating is given by negative p. So here we have negative x times the partial derivative of g, which was the graph of our function with respect to x, which would be negative 2x, plus the second component, minus the second component of our vector field q, which was y here, times the partial derivative of g with respect to y, which would give us negative 2y, plus r, the third component of our vector field, which is z, integrating with respect to area. So to evaluate this double integral, let's see if we can set it up as an iterated integral. And before I do, let me simplify the form of my integrand. So here we've got the double integral over d of, simplifying, we have a positive 2x squared plus 2y squared plus z. Now this is a double integral. It should only depend on two variables. So recall that z here, for points on our surface, z is defined by this function g of x and y. That is 4 minus x squared minus y squared. So if we replace z by the equation of that surface for points on that surface, 4 minus x squared minus y squared, we have the following. Or simplifying a bit further, we have the double integral over d of 4, our constant, plus when we group our 2x squared plus 2y squared with the minus x squared minus y squared, we're left with just a single x squared plus y squared. So to evaluate this double integral over the disk D, which was shown here, that is the disk centered at the origin of radius 2, we might use polar coordinates to set up our iterated integral, since it is part of a disk. So here, our outer integral with respect to polar coordinates, that is with respect to theta, would be from 0 to 2 pi to get all the way around our disk. And then the inner integral with respect to r would range from 0 to 2, since this was a disk of radius 2. Then converting our integrand to polar coordinates, we have 4 plus x squared plus y squared becomes r squared. And the differential of area in terms of polar coordinates is given by r dr d theta. So we have then the following. If we integrate our outer integral with respect to theta first, well, we see our inner expression with respect to r will be constant with respect to theta. So we have our constant integral from 0 to 2 pi for r plus r cubed when we distribute our r times dr. Times the constant length of that interval, the theta interval, which was 2 pi. So now evaluating our integral with respect to r, we have 2 pi times 2r squared plus r to the 4th over 4, evaluated from 0 to 2, which leaves us with 2 pi times, when we plug in 2 for r, we have 2 cubed, or 8, plus 16 over 4 is 4, minus, when we plug in r equals 0, we have 0. So we're left with 2 pi times 12, or 24 pi. So that would be the flux over S1, the upper part of this closed surface S. But to get the total outward flux across that surface, we still need to integrate over this bottom portion, S2. That is the flux integral oriented downward across this disk D, or S2. So let's think about how we could describe S2 as the graph of a function of two variables. So for our second part here, we can think of S2 as the graph of the function g of xy equals 0. So remember, this surface S2 lies in the plane z equals 0. So if we think of it as the graph of a function, it's the graph of the 0 function, which lies in the disk D which is defined as x squared plus y squared is less than or equal to 4. All the points inside the circle centered at the origin of radius 2, which lies in our xy plane. So our flux across the surface S2 would be evaluated as a double integral over this disk D of, let's think about the function that we're integrating here. So we would integrate negative p, which was x, the first component of our vector field, times the partial derivative of g. Now for S2, our g function is just 0. So its partial derivative with respect to x would be 0. Then minus q, the second component of our vector field, which was y, times the partial derivative of g with respect to y, which would be 0. And then plus the third component of our vector field, z, with respect to area. So here we have the double integral over d. Oh, and one thing that I should mention here, since the surface S2 has the downward orientation, we would need a negative in front of this double integral. So recall that formula was making use of the upward orientation. So if we're taking the downward orientation, we need a negative out in front to reverse that orientation. And what we're left with is 0 plus 0 plus z. But the value of z on the surface S2 is 0. Remember, S2 lies in the xy plane where z is equal to 0. So we're left with 0 for that third component. So this double integral of the 0 function gives us 0. So to get the flux across this solid, we would add the flux integral across our first surface and the flux integral across the second part of the surface, S2. And we're left with 24 pi plus 0, or just 24 pi. Okay, so in this last example, we started looking at how we can evaluate a flux integral over a closed surface if we think about the closed surface as consisting of maybe two or more pieces or two or more surfaces which are smooth surfaces, and then evaluating the flux integral over each subsurface and taking that sum. So we see even for this example, where our surface S might be the union of just two pieces, it can start to get a little bit tedious. And at the end of this chapter 6 material, we'll get a nice result which makes evaluating these flux integrals over closed surfaces much easier.